Okay, the next section is about eigenvalues and eigenvectors. You see eigen as like a prefix for a lot of things in linear algebra. After a while, you just kind of roll your eyes and say it's eigen something or other. So that's the title of this, but it's a very important part of linear algebra. These seem to show up all over the place in linear algebra. There's very interesting use cases for them, especially when you're working with data at scale. So I want to take a look at how these are made. First off, though, let's go through some example use cases just to give a flavor for what you can do with eigenvalues and eigenvectors. One case in terms of geometry, think of doing image processing or video processing. You want to be able to take an image and scale it, rotate it, stretch it. So if you can take a matrix defining a shape, different points on an image, then you can apply, in this case, eigenvalues to be able to determine how to reshape that. Essentially, you can build up another matrix out of eigenvalues to be able to do a transformation. In another case, in terms of statistics, we see eigenvectors being used a lot. We'll do an example a little bit later on, but in particular, there's something called principal component analysis. It's very closely related to, say, cluster algorithms. But the idea is that if you have a lot of different variables, a whole lot of data, you want to be able to represent a matrix that has the covariance, how those different variables are related to each other in all the different observations. And from there, then you start to identify the eigenvalues and eigenvectors in the covariance matrix, basically peel them off, take them in descending order. The biggest eigenvalue peels off the most variance possible out of that data. And you look at it again, you peel off the next one, peel off the next one. It's a way of doing something called dimensional reduction. We use that a whole lot. As another example of eigenvalues, eigenvectors, there's something called eigenfaces. And this comes out of some really great work from 1987 where, well, actually the paper was by Sirovich and Kirby. It was entitled Low Dimensional Procedure for the Characterization of Human Faces. Essentially, if you take a look at, say millions of people's faces, you can break it down into building blocks. Common things that you would have in facial features, kind of like when they're doing a police drawing, when they adjust the knobs on a police drawing. You can basically rebuild a face from these different component building blocks. And that's a way of taking an image of a face, decomposing it into different parts, and being able to do recognition by looking at the eigenvectors. Another case is in graph analysis. Say you've got a social graph. Here I'm actually taking a graph I think that came out of LinkedIn. They use a project called Gephi for something called InMaps at LinkedIn. I don't know if you've ever had that calculated, but it's a free service they provide that shows your social graph off of your LinkedIn connections. So eigenvalues and eigenvectors come in very handy for analyzing the structure of large graphs. It's a way of measuring a complex graph, and I can tell you some very useful things about graphs. Suppose we have a square matrix A and some non-zero vector x, and then some scalar lambda. We can write an equation ax equals lambda x. So for matrix A, the vector x is going to be the eigenvector, and the scalar lambda is going to be the eigenvalue. Now, it's possible that you could have multiple solutions for lambda and x. We'll get to that later. But in essence, from matrix A, you're going to have some set of eigenvectors, some set of eigenvalues. Okay, and the way that this is determined, if you want to go through the math of how this is constructed, let's say that we start out with ax equals lambda x. And if we want to try to solve that and figure out what the lambda and the x are, one thing we can do is first move all the terms over to the left-hand side. So we've got a minus lambda x equals 0, taking the lambda x and moving it over to the left. And let's say also that we can multiply every term by the identity matrix, I. So a times ix is the same as saying ax. And then we've got minus lambda ix equals 0. 0 times I is 0. OK, so now we can take and regroup that, put in the parentheses, and say we've got a minus lambda I, quantity, times x equals 0. And now a really cute trick is we can take and say that the determinant of a quantity, a minus lambda I, equals 0. We know that vector x is non-zero, so it can't be 0, so the other term has to be 0. So at this point, we could take and find the determinant of that quantity there, a minus lambda I. And from there, we've got one equation, one unknown. It's going to be a polynomial. We can solve for the root. So we call this a characteristic polynomial of matrix X. We do this whole construction there with like a minus lambda I. So I've shown some examples here. We've got a matrix. It's got 0, 1, negative 2, negative 3. We've got lambda I, which is just basically lambda eigenvalues along the diagonal, but zeros everywhere else. And so then we can come out with a minus lambda I is this other matrix here, 0 minus lambda, 1 minus 0, negative 2 minus 0, negative 3 minus lambda. If we take the determinant of that, we end up with a polynomial. Down here, it's going to be, if you go through and calculate it all, it's going to be lambda squared plus 3 lambda plus 2 equals 0. Now, if I solve for the root, lambda as a variable there, if I solve for the root of that polynomial, calling back to what we did earlier in algebra, we can refactor this and say that we've got lambda plus 1 times lambda plus 2 equals 0. So the two possible solutions are if you've got lambda equals minus 1 or lambda equals minus 2. Those are your eigenvalues. So given those eigenvalues, you can plug them back in and solve for the corresponding eigenvectors. Find out what the corresponding two values of x are. Without going into all the gory details in the math, we can use linear algebra in Python. Makes this a lot easier to compute. OK, so I've got some Python here using NumPy again, and I'm going to define my matrix A. And cut and paste that. So if I take a look at A, I've got this same matrix. And now it's just one call. I'm going to use NumPy, again, with linear algebra package. I'm going to call the Eig function on A. Blam! And it's going to come back with a couple parts. The first part is an array. We see our eigenvalues, negative 1, negative 2. Right? And then we've got the corresponding eigenvectors. One of them is this vector here, 0.7 and negative 0.44. And then the other eigenvector is negative 0.7 and 0.89. So it's a really simple thing to be able to find out eigenvalues and corresponding eigenvectors.